What's the main difference between analog and digital signals? Whereas an analog signal, such as a record of the air pressure changes that make up sound, whereas that's theoretically at least continuous, both in time and in the variable being measured, such as pressure in this case, that's continuous with an analog signal. With digital signals are inherently discrete. A digital signal is obtained by sampling the analog signal that we're interested in, such as the air pressure. But there's a serious trap that I want to alert you to with doing that. Suppose we have a signal such as the one in front of us here that we want to turn into a digital signal. So let's just recap the process. We have our signal, whatever form that is, such as a sound wave. We take samples of it regularly, and then that's our digital signal. That's all it is. So how does our MP3 player, for example, turn that back into sound? Well, it takes the samples that we have recorded and stored in some sort of format, and then tries to recreate this original wave that the samples came from. So that's the process. So we have to collect some data, some samples of the wave that the computer, the MP3 player, whatever, later reconverts back into this original wave. Okay, so let's have a look at this process here. So here's our wave with a period of 2 pi, and with the slider here I can sample at different rates. So when we talk about sampling, we are talking about how often we record the value. So we can talk about the sampling period, how long between samples, or we can talk equivalently of the sampling frequency. How many samples do we take per second, or whatever it is we're talking about. Here I'm just going to talk about sampling period, and I'll start with a sampling period of 1. So we're going to sample 1, 2, 3, 4, 5, 6, 7, right the way along. Okay, so let me do the sample. There we go. I've sampled my original signal. I've stored that, and then I want to play the original sound back. What happens? The computer or the MP3 player takes the samples and tries to get the original signal back. Let's see how it would go on this one. Okay, well that's very nice. Let's just try another one now. Let's sample the sampling period of 2. When I get this thing. So I take my sampling period up to 2. And now I'm going to be doing sampling at 1, 3, 5 and so on. Let's have a look. There we go, there's my samples. And I'll recreate this one to see what sound I get out of my MP3. Nice, there we go, no problem again. So, well, let's reduce this again. Let's collect even less data. Oh, what's going on here? Now things are getting a little bit interesting. The signal that's being recreated is not quite the same as the one that produced the sample. What happens if we go even further up? Oh, things are getting quite serious. And further up. And you can probably see now what the problem is. If I don't sample often enough, I just get such a low sampling, or such a small number of samples, that the sine curve, in this case, that I fit between those sampled points, is way different frequency from the one that gave them, because I've lost too many data points. I've lost too much information. I mean, you can imagine if this original one was a sound wave, this is a certain frequency, and if I only sampled at this rate, then the recreated one would be a much lower note, much lower frequency. So completely distorted. That would be terrible. So this is the warning then. We don't want to collect too much data, because that just wastes storage space. That's precious. But we don't want to sample too infrequently, because then we lose information and we get rubbish out. And this, when the recreated signal is way different from the original one, we actually call this aliasing, and it's a bad thing to do. How can we stop aliasing? How can we stop this happening? Let's just have a look at our sampling period slider up here and just drag it back. So 5's no good, terrible. 4 is pretty shocking. 3, that's when things are starting to come unstuck. It's not too flash, but you can see it's not so different from the original one, particularly the frequency. There's a slight phase shift, but and if we go down to 2, that's when things were just wonderful, and 1, of course. That's great too. Okay, so it was sort of around 3 that our problem started. What do you notice about 3? What's 3 got to do with it? Look at the period of our original signal. It's about 6. If we started sampling with a sampling period of 3 or more, we get into trouble. And this is actually a very important principle in all sampling of digital signals. Our sampling period must be at most half the period of the original signal. So just going over that again, the original signal had a period of 6. Our sampling period must be less than half of that. So we must be sampling with a sampling period of 3 or less. So 1 or 2 was great. 3, things were getting a bit marginal. And after that, it was just all over. So a sampling period less than half that of the original signal. So we've got to be taking at least 2 signals within a whole period. That makes sense. That's quite reasonable. This is actually called the Nyquist criterion. And the cutoff, the threshold, is called the Nyquist frequency. That's the period we have to be sampling at. Now, as I said before, if this was a sound wave and we got aliasing, we would get a much lower note, a lower frequency. That would distort our sound horribly. In imaging, which we're going to be looking at very soon, there are some classic examples of aliasing when the data has not been sampled frequently enough. Here's a typical one with imaging. Medical imaging. We were trying to image a head here, and look where the nose has ended up. And you can imagine I mean, this is sort of obvious that something's gone wrong here, but if you're not an expert, and sometimes even if you are, if the changes are very subtle, imagine if that was closer. And so this thing, it seems to be attached to the back of the head, so that's a nose at the back of the head. Well, that's obviously not realistic, but it mightn't be a nose, it might just be a very small imperfection. And it might start looking like a tumour or something wrong in the brain, and it's just an artifact of poor imaging. So you must be very careful never to disobey the Nyquist criteria. Here's another one. Here's an example of a slice through the brain, well imaged. That's what it should look like. This is when it was done without enough sampling. Not nice. So this Nyquist criterion, it's not just a nice thing to think about or to have heard about. It's something that if you have any control over the parameters of your sampling, you must take very seriously. So let's look now at digital imaging. Well, you're probably not surprised to know that what we think of as a digital image is something very different from how the computer sees it. To a computer, a digital image is just a collection of numbers. So something like this would be closer to a computer's view of an image than the final product we look at. Basically, I have divided my image, if I think of the image as the big square taking up nearly the whole screen, the outer square, if that's my image, I've divided that up into lots of small squares called pixels. These are what pixels are. Each pixel has a number associated with it. I've printed the number on the screen here on each pixel for you to see. And in this particular image, not particularly exciting one, the values are either 255 or 0. Then the computer stores that value along with the address of each pixel, and that's it. That's a digital image. For example, the pixel with the address 5 along and 2 down, like many of the others, it has a value of 255 stored in the computer along with the value and the address of every other pixel. We then use software to change these values, the 255 or 0 or whatever else it might be, to change these numbers back into an image as we expect an image to be, not just a collection of numbers. Generally, software assigns 1 byte of memory for each pixel. So there are 256 different values, different possible values for each byte. In other words, for each pixel, the values it can have can range between 0 and 255. Because that's, we start at 0, we have to end at 255, total of 256 values. And here's my maximum value, 1111111, and that turns out to be indeed 255 in decimal. This binary value converted back to decimal is 255. All zeros is the smallest value, of course 0 in decimal. So that's our range, 0 to 255. And if each pixel has 1 byte, 256 possible values, and these values represent different shades of grey. That's the key to it. Let me show you now what that first image below would look like. So let's have a look at the image. That's the digital image as sort of as the computer would have it. There we are. So that's starting to make sense now. We could get smart and add a nice border around. Let's have a look so let's go back to our digital image, because this is where all the processing happens at the digital stage. The digits, they are what get edited in any photo editing software or anything like this. It's this that changes. We change the numbers, we change the picture. So here, remember these before were all 255, so I've changed the outside border to 128. So half grey, well, half black, half white, grey. Let's see what it looks like when it's then reconverted to something visual. And there we have it. So I hope this helps you to see that a digital image really is just a collection of digits of zeros and ones. And these can then be converted if they are used to represent a level of grayness or for a colour picture, colour image, different colours and so on. Then it can be used to display a visual image as we understand it. But really it's just a collection of zeros and ones. And I hope too that this quick look at a digital image shows you how pixel size determines the graininess or the sharpness of the image. To get a lot of detail, obviously we must have small pixels. Big pixels are rather clumsy. If we have small pixels, then we need more of them to cover the same area. And that's why our digital cameras like boasting how many megapixels they offer for an image. But of course, the more pixels there are, the more information has to be stored. So there is always this trade-off between getting a wonderfully sharp image and using lots of storage.